Welcome, and today we're going to talk about PNP Bipolar Junction Transistors, or BJTs. In a previous lesson, we introduced BJTs, but we focused mainly on the NPN type. NPN and PNP BJTs are extremely similar in some ways, but they do behave slightly differently, and understanding these differences ensures you can confidently choose the right transistor for your project. Before we jump into things, I just want to, again, thank Digilent for their support in making this and all of the DC circuits lessons possible. I'll assume that you already understand how an NPN BJT operates, either from our other video or some other way. If you're not familiar with BJTs in general, please go check out our other video and then come back to this one. Unlike an NPN transistor, which has two N-type materials sandwiching a P-type material between them, a PNP transistor has two P-type materials with an N-type material between them. This difference in material is why they act differently. With NPN transistors, you may see how a small current flows into the base and exits through the emitter, controlling a larger current from collector to emitter. However, in a PNP BJT, the direction of current flow is reversed. Here, a small current actually flows out of the base, controlling a larger current flowing from the emitter to the collector. You can think of it as an inversion of our water spigot analogy. The concept is similar, but the flow direction is reversed. Just like with an NPN transistor, we have our three terminals: base, emitter, and collector. But with a PNP transistor, the emitter terminal is at a higher potential, or more positive, while the collector is at a lower potential, or less positive. This is opposite to the NPN transistor, where the collector was more positive. In this case, the base is also at a lower voltage than the emitter, allowing current to flow out of the base. Now, with the emitter and collector fulfilling different roles, this can cause a bit of confusion with operating regions. As you remember from the BJT overview, we have the cutoff, saturation, and active regions, and the same general concepts apply, but the polarities are reversed. Cutoff region is like having your spigot off and no current flows because the emitter-base junction isn't forward biased. In the saturation region, where the BJT acts like a fully closed switch, the base needs to be slightly lower than the emitter, forward biasing both the emitter base and collector base junctions. Finally, the active region is where the BJT acts like an amplifier. With a PNP BJT, this is where the emitter base junction is forward biased, meaning that the base voltage is slightly lower than the emitter. But the collector base junction is reverse biased, meaning the collector voltage is even lower than the base. In regards to beta, it still describes the ratio between collector current and base current for a PNP transistor. However, remember that in a PNP transistor, these currents flow into the transistor through the emitter and out through the base and collector terminals. So with all of this information, you may be wondering why we would ever need a PNP transistor. It comes down to which side of the supply you are switching. For low side switching, you'd like to use an NPN. In other words, if the load is tied to the positive rail and you insert the transistor between the load and ground, you are interrupting the return path. An NPN turns on when its base is driven about 0.7 volts above its emitter, which is tied to ground, so it is the natural choice here. But for high side switching, we'd like to use a PNP. So if the load is referenced to ground, and you need to connect or disconnect it from the positive rail, the transistor has to sit between the power source and the load. A PNP conducts when its base is pulled just a few hundred millivolts below its emitter, which is attached to the positive rail, making it perfect for this high side role. A quick practical example is if you have a motor you'd like to switch on and off. Assuming a 12-volt rail, if you wanted to use an NPN, you'd hook that rail up to your motor, connect that motor to the NPN BJT, then connect that to ground. However, if you'd like to use a PNP, you'd connect that to a 12-volt rail directly to your PNP BJT, then to your motor, before finally connecting to ground. Of course, in reality, unless you're just trying to cobble something together with the parts you have, you'll choose between NPN and PNP based on your design needs, not by which part you want to use. Either way, just remember to use an NPN when you're breaking the connection to ground, on the low side of things, or a PNP when you're breaking the connection to the positive supply, or on the high side of things. And that's all we're going to touch on PNP BJTs for now, and hopefully this helps you understand PNPs better, how they're made, and when you would want to use them. As always, you can support our content by going to Digilent and see if they have any tools that can help you. If you do purchase something, don't forget to use the CircuitBread discount code on digilent.com, which will get you another 5% in addition to their academic discount. You can find that code on the Digilent Friends page at CircuitBread.com. If you found this video useful or helpful in any way, please give it a like, subscribe to our channel, and we will catch you in the next one. Take care.
Hey, I hope this tutorial was helpful. Did you know that CircuitBread.com also has more useful engineering content? In addition to the tutorials, textbooks, tools, and other things, we have dozens of EE FAQs that explain quick, standalone concepts that are helpful for electrical engineers. Go check them out.